Okay, guys, I want to talk a little bit tonight about lidar. What is lidar? Where does it come from? And how we can use it in GIS. lidar is an acronym. It stands for Light Detection and Ranging. The underlying principle is you can determine the distance by uh, how much time passes between uh, sending out a pulse of light and when that pulse of light is reflected back. That's basically all it does. It shoots out a tiny little laser emission, and then it calculates the time until that pulse of laser light hits something. Um, there's other terms for it used in different places. In Europe, they call it airborne laser scanning or airborne laser mapping. Sometimes you'll hear it called laser altimetry. And of course, laser is also an acronym for light amplified by stimulated emissions of radiation, and it is simply an intense, narrow, coherent beam of light in a single wavelength. And basically, what happens is instead of um, dispersing much the way ordinary light does, it disperses at a much, much lower rate, and so it stays in a concentrated, narrow beam for much, much longer. And that's what makes this process sort of work. Now, in order for this all to work, there's a bunch of things that have to sort of go together. The first is you've got to have a ability to measure the angle of the laser direction. In other words, this system has to be mounted with some sort of a gyroscope. Second is you need to know the location of the laser system. In other words, you have to have some sort of very accurate differential GPS and an inertial um, management or inertial navigation system. And you have to have that because you have to have this orientation of the laser system. In other words, not only do you need to know um, where it's pointed and where it's at, you need to know the direction it's moving and how it's moving. Um, because you have to have the exact position of all these signals and take into account the movement of the aircraft. And then basically it kind of works like this. You're flying at some altitude, you're taking a measurement of a path across a certain area. The system is sending down all these beams and it's monitoring the response in this zigzag pattern like this. First lasers were developed in '58. They used lasers to measure the distance to the moon from a mirror that was placed there during one of the space missions in 1964. By the 80s, they had laser profilers, and by the 90s, they had laser scanners, and then commercial firms like Azimuth and Optech and Saab began developing this technology. And this led to a rapid adoption because it was so profound in terms of what it could do. By 1995, there was only 3 systems. You roll ahead 5 years to 2000, and there were 20 new systems that year alone. By that time, there were 58 different lidar systems in total that were available for folks to use, and I'm sure that number has only increased since then. I have a couple different types of systems in lidar you need to be aware of. When we're looking at terrestrial or land features, we often use just an infrared. It gives few returns, if any, over water because obviously water absorbs infrared light. So the infrared systems don't provide you much information there. Um, but if you want to know some information about water, they do have a blue or a green colored laser system that they use. And the depth penetration that this system will get in water depends entirely on the clarity of the water. But in general, you can go to about 3 to 4 times the depth of what you can see with the naked eye. So if the water is extremely clear and you can see 20 feet down, then you can anticipate measuring somewhere between 60 and 80 feet deep with this system. What are the characteristics of LiDAR? Well, you can fly it under clouds because you literally fly under clouds. But you can also do it when it's cloudy, it's not really a problem. Overcast conditions don't interfere with it so much. And you can do it at night. You're not dependent on daylight or cloud cover, so that's good. It can be flown from a fixed wing aircraft or from helicopters. You can fly it when there's leaves on or leaves off. It doesn't matter. When you look at stuff like photogrammetry, it requires these two separate views of the ground, and a lot of times that's hard to get when you have a lot of vegetation. But that's not a problem with lidar. It penetrates through things and around things and can find those tiniest of cracks, and that's what it does. This is what a slice across lidar data would look like, and you'll get some idea what we're talking about. This is across the forest, and you can see all those hits you get up there at the top um, from the treetops. And then as you go down, you can see how you get less and less hits as there's less and less limbs. And then a funny thing happens. You hit the ground. Now there's a couple of points like there around 48 and 58 that appear to be below the ground surface. That could be a signal bouncing off of something midway down, or some sort of a delay in the signal coming back, or it could be a hole, or it could be any number of technical glitches that are interfering with it. And so there's a couple of things that has to happen when you have data like this. One is you got to clear those things up, and two, you really can't do much with 8 billion, jillion, trillion points, except look at it in some kind of a context like this. And so you go through some post-processing where you would basically create a digital elevation model of the surface from the top of the trees, and then a digital elevation model of the the surface would be at the bottom, the terrain would be at the top. But you could map both. You could map that the digital surface model from the trees and the digital terrain or elevation from the ground below. So what are some of these characteristics of these instruments, and what do they look like? Well, let's talk about this laser beam, this footprint. It is a function of a couple of things: the divergence or the angle, the height. But typically what we're looking at is 0.1 to 1 meters. So you're looking at getting a measurement every 10 centimeters to a foot, or 10 centimeters to a meter in space. Number of pulses per second is pretty high. Laser scans in a zigzag or other pattern, and it typically goes out to like a 70-degree range. So it's not only going straight up and down, it's also going at angles. It's looking for any way that it can get through to measure that surface. Your root mean square error in terms of vertical measurements is about 15 centimeters. Your horizontal root mean square error is somewhere between 10 and 100 centimeters, or it's less than a meter. In addition to this elevation attribute, you can get a great deal of intensity information. We looked at those cross-cut view of all those forest trees. You can get some idea of the thickness of the underbrush or understory. From that, you could tell a lot of things. For example, if you have a lot of leaves and limbs at a very low level, that is an indication that you probably don't have a really large deer population, because deers are browsers and they will keep all the leaves and tiny little sticks trimmed up and ate up, everything below about 5 feet. The return measurement, you get this direct signal, which is a single measurement, and then you get this full waveform measurement, which is a continuous measurement. Just different ways of measuring it. So let's look at what that kind of looks like. Chopper flying, lidar sensor underneath, shoots down a laser pulse, hits something, hits something else, hits something else, hits something else, and that's the end of it. As it's measuring these things, the first thing it has is this echo reference, or like when it's sent. The first sort of bounce back that it gets from that signal is the very first surface it hits. The second is something in there a little more. The third is something that's underneath of that, like a smaller tree or brush. And the last one is the ground surface. By measuring the time on these signals, you can calculate out the height. And if you know the exact position when the signal was sent and when it was received and the angle and all that other stuff, a combination of time and trigonometry will give you an elevation value for each of those points. When we talk about a first return, we're talking about a digital surface model. This is the top of vegetation, buildings, or in some cases the ground. The last return may be the ground. It's usually your best candidate for the ground, but it's still got to be filtered for non-ground points. So you have to take out buildings and roads and fire hydrants and people and dogs and cows and potholes and whatever else. Intermediate returns are primarily only used in forestry as a means of evaluating timber stands. Number of measured returns. Early instruments recorded one return, first or last. You decided what you want. The modern one can record up to 5 returns, and so that allows you to get this sort of cross-sectional measure, if you will, from the surface to the ground. So let's talk about these continuous waveform instruments. This is a little bit different type of system. It measures a continuous signal, and it usually has a larger footprint, like 30 meters. It's often referred to as a large footprint system, something like Slicer, an aerial system, or the vegetation canopy lidar mission was something that was going to use this. It was a NASA program, but it got canceled. They give an excellent representation of the distribution of vegetation in a canopy, because basically it's just continually measuring at a larger area, and from that you get a much more detailed look at the composition of that vegetative canopy. So here's what that would sort of look like. This is a scanning lidar image of canopies using an echo recovery system, the Slicer system that we just mentioned lightly. And you have a one-way travel time, and then you have the return energy. And so it sort of gets this, it's like a feedback thing. And you have this normalized cumulative return. And from this function, you can get an idea of, at the top of the tree, it's not real thick, and then as the cumulative return amount increases, you know, oh look, yeah, hey, we're getting something. And then it drops off, and then you get another spike, and that's when there's something else there going on. And then after that, you just get some noise. And basically from that, you can sort of get an idea what that canopy looks like and how that would relate to the various trees and things. Post-processing is basically where we take all the projection information and do the conversions. We interpolate to get our surfaces. If we manually post-process, we're doing it to remove errors and points that are on the ground, things like trees and birds and bowling balls left in the yard and that kind of stuff. Below ground things, stuff where you have a double bounce path, you know, so it gives you that extra distance that shows up below. In general, the cost of acquiring lidar data is only 40% of the total cost of the project. 60% is this. This is a lot of work. It is becoming increasingly more automated, and this is increasingly more often shot with more and more sophisticated equipment that can literally do most of the post-processing as the aircraft is collecting the information. So when it lands, it has not just raw data, not just the LAS file, but product. And by product, I mean digital elevation models, digital surface models, that kind of stuff. As far as the classes of LiDAR data analysis, generation of digital surface models, bald earth mapping or digital elevation models, which is the earth without vegetation or buildings. It's also useful for change detection, whether we're looking at how and where roads have been put in, where trees have been cut down, where valleys have been filled, where mountaintops have been removed, where trees have grown taller or haven't grown taller, where lakes have gotten bigger or smaller. Change detection is important, where super volcano calderos have expanded or not. Is the supervolcano under Yellowstone, is the deformation of the surface of the Earth increasing since the last time we flew this or not? These are all things you can do with this. Object identification. Um, there's a lot of stuff you can do with this with CAD, as well as there's some specific software systems designed with power line management. It allows them to fly lidar and record the position of their power lines and any thing relative to it in terms of potential obstructions or things that need to be cleared, like how often they have to go cut the brush away, that kind of stuff. Lots of opportunities to use this kind of technology for many things. And then, of course, in forestry, you can ascertain a lot about the forest from using lidar. When we talk about the format in the software, well, that's a little bit of a problem. LiDAR is point-based and most remote sensing software is raster-based. And GIS systems are vector-based, but they're not super set up for these kind of large data volumes, and so it can be an issue. To interpolate from a LiDAR data set to a DEM is a loss of data, because you a lot of times have multiple values for one cell. And it creates new data points in empty cells where you don't have anything, and so that's a bit of an issue. As far as the applications, atmospheric LiDAR, there's a degree of scattering related to the profile of what you're doing in terms of the composition of the atmosphere that day, the temperature, the wind. All these things can have some impact on atmospheric LiDAR. From an oceanographic standpoint and how you can use it, you're limited in the depth that you can use this with, and then you have to deal with obstructions as well as changing plumes of things like sediments. Terrestrially, there's a wide range of applications. It is super powerful for identifying topography underneath the vegetation canopy, and so much more so than you could do with photogrammetry or any other means. You can get really accurate elevation models of the surface under vegetation, full canopy, tree growth in the middle of summer, taken at night or at day, when it's cloudy, when it's not. It's pretty awesome. Give you some idea what we might be talking about. The top is a high resolution digital photo of a particular 3D rendering of a hillside, and there's some things there you can see and there's some things there you cannot see. But when we shoot LiDAR on that and we create a terrain surface model and we strip away everything down to those last returns and we look at the bare surface, you can see the network logging roads and tiny little valleys and runs that go down the sides of the mountain that you cannot see through the vegetation. Pretty impressive. Forestry applications. Here we're looking at two trees. One's bigger than the other. What could you tell from that? They're both relatively the same size. If you have the right skills in forestry, just by looking at the shape of that canopy and how far apart they are, you might be able to tell, at least at some level, what species of trees we're talking about. More importantly, if you monitor things like change using LiDAR, you can look at the same trees over changes in periods of time. And you can see things like down there on the ground, we've got a bush. Bush is the technical term for stubby little tree that should be cut down. in terms of forestry anyway. Bushes are fine in your yard. But if we look at the top of that tree, you can see how you've got the red dots, and then above that to a slightly higher level you have some yellow ones, and then above that to an even higher level you have some green ones. What you're seeing here is the growth of the tree. If you know, for example, that with some certainty you can predict the size of a log based on the height of a tree in a forest, where you have some information, like the trees are this big around, they're this tall, it gets this much taller. If you know how much bigger that means the tree has to get around to do that, or to support that, or what typically goes along with that, you can just go back out and do these flyovers, and lo and behold, you'll have a really good idea of the board feet of timber that's there. And so, for example, tract of timber comes up for harvesting. They're going to sell it to the highest bidder, and the logging company or the sawmill or whatever it is that you work for, they want to know, what is this actually worth? Well, you could look at some remote sensing stuff and get some idea of the composition of the trees and say, well, it's 90% hardwoods, it's 10% softwoods. Okay, got that. How many board feet of timber? Well, if you can use something like this to get an idea of the maturity of those trees, you can pretty quickly then come up with a number and convert that out and say, okay, it should be this much board feet, it should be worth this much money. You can then make a reasonable guess at what you're willing to pay for it. Whereas other people may not have this capacity, and they may not have the time to send someone out to do it the old-fashioned way. It's something called cruising timber, where you go in and you measure and count certain numbers of trees along transects and do some math to extrapolate out what you think is there. It's a tried and true method, and they understand the accuracy of it pretty good. But you may not be able to afford to get that done in time to make this, and so you may be making a blind guess and say, okay, well, we think it's worth this, and so we'll offer this much money. And what happens is you might be offering significantly less than what it's actually worth, in which case the person who has this information makes a more accurate assessment, and they end up with the timber. Or, worst case scenario, you make a guess and you overestimate the quantity of wood there, and you end up paying a lot more than what you should, and you'll never recoup your money after you cover your overhead costs. In this example, from 1998 to 2003, this particular tree, grew in height by 3 meters.